Hi, I'm Jim Pasmore. I'm a consultant for the handheld spectrometer industry. I've been doing this for about 45 years. I started out with a company called Niton, which developed the first handheld XRF, X-ray fluorescence analyzers, and I was a part owner of that. Niton was sold to Thermo Fisher Scientific, and it resulted in Thermo Fisher Scientific continuing the development with the result of this ultimate analyzer, the Niton XL5+. This Thermo Fisher Scientific analyzer is the smallest, lightest, fastest, and among the highest performance analyzers ever built. And I'm really happy to say that because I've been around the industry long enough to know that some of these in the old days were 20, 30 pounds and took 30 seconds for analysis. What you'll see when we do some operational testing on this is that we get results in seconds. It's lightning fast. It's an elegant design. It's got the measuring end right here. We got a flip screen so that you can see the camera view on the distance. You also have a micro camera for close-up. And we can adjust this to the angle that's best for wherever we're operating. The ergonomics is great. It's got a little safety strap that you can put on your wrist so that you don't drop it. And I've got it connected right now through a USB cord to a computer so that you can see everything I see on this screen. And so next we're going to take you through some of the operational features of the analyzer, and then we'll test some metals. Okay, so I'm going to take you through some of the operational features on this analyzer, starting with settings. So if I tap on settings, you can see we can do a system health check here and look at all the capabilities of the analyzer in terms of buttons, in terms of temperature, in terms of calibration. And it does have a calibration standard built into the front of the analyzer so that you never lose it. All you have to do is tap system health. It'll go through the complete check and it'll check the calibration as well. In addition, we have the general settings, date and time, all the device information, all the licensing information, lots and lots of different languages for you. Then we have camera usage. I have it disabled at the moment, but you can turn the camera on and take pictures at a distance, so whatever you store with your analysis, you have a picture of it as well. Connectivity allows us to use Wi-Fi, data transfer settings where we can pick up what we want to export, averages and so on. And we can also go to Bluetooth and GPS. It's got quite a number of features, including the capability of secure transfer via Wi-Fi, printer settings where you can have a portable printer connected, have that hooked onto your belt and print out directly, or send it to your computer and print from a file that is sent to the computer called a encrypted file. That encrypted file allows you to have absolute security on everything that you print out. It's CFR 21 Part 11 encrypted so that nobody can change the data. It also, at the same time, can print out a CSV file which you can use to adapt to your operations. You can also print certificates from here with your company logo on there. So let's continue. Profiles. Here you can take a look at all the different applications that are built into the analyzer. We've got general metals, precious metals, electronic metals, coatings, mining applications, soils, plastics, industrial paint, spectral fingerprints, and so on. Additional applications can be added on, so you have multiple modes. Obviously, you don't have to have every mode. That does increase the price. But the standard system comes with at least one or more applications, depending on what you require. And then we have the libraries. Libraries include standard libraries that come from the factory, the XL5 Library 1.1, the Deutsch International Norms, and the Great Britain Library. Additional libraries can be added. As you can see, I've added several onto mine just to try out different types of applications. Then beyond libraries, we've got threshold sets that allow you to set a flag whenever any of your testing shows a consumer good or a restriction of hazardous waste, ROS as we call it, levels above the required minimums or maximums, and you can have it flag those. Data field sets, here's where you can look at what comes from the factory in terms of default data fields or add your own data fields in. Network shares, this is where you can set up your network and your domain and usernames and so on. Everything you need to share the data with your corporation if that's the way you want to do it. And then maintenance itself, here's the system check, safety features, such as proximity button on the front that you have to have pressed in before you can take a measurement, or you can have a secondary trigger requirement, or what's called an easy trigger. That's a momentary touch where you just touch the trigger instead of holding it, and it takes the measurements. And here's your Wi-Fi certificates. So let's go to the next operational area, the data. Here we see all the data that's been collected since I've been using this analyzer, 2,089 measurements. And if we look at number 2,088, for example, it's a low alloy steel that I just measured, and all the data for that is recorded, including the element, the percentage that was determined, and the 2 sigma, or 95% confidence limit for those measurements. We also can operate with the wrench to change the alloy display, sort units, averaging, and so on. So quite a capable system in terms of operational features. So we're ready to go to analyze. You can see that the camera is disabled. Otherwise, I could take a picture by tapping on it. You can see that we have the ability to go in and look at various areas of the modes for testing. We can also adjust our settings. Right now I have it set up for scan times of 3 seconds on what's called the main filter. That's the filter you're going to be using 99% of the time. The main filter tests everything from atomic number 22 on up to 92, depending on the application mode. The light filter is used for elements below atomic number 22, typically from atomic number 12 to 22, so elements like magnesium, aluminum, silicon, sulfur, phosphorus. And it's required for certain alloys where you don't have a full fingerprint with just the heavy elements, as we call them, but you require light elements to be added in order to finish off the application of testing that alloy or testing the soil or testing in mining, whatever the case may be. So let's go ahead and look at data entry. Here you see we could put a sample in, a sample name. We can just tap in the letters, save it, and go ahead and start measuring. Okay, so let's test some samples with this analyzer now. Let's put on this safety strap. And what I have laid out here is an alloy application. Here we have stainless steels, we have nickel-based, we have low alloy steels, we have titaniums, aluminums, and coppers. A pretty wide range of possibilities. The alloy application is the most popular use of this analyzer, and it's probably, I would say 50% or more of all the 60,000 analyzers out there, these Niton analyzers and Thermo Fisher Scientific Niton, are used for alloy applications. So we'll start with the most popular alloy in the stainless steel group. It's called 304 stainless steel. It consists of 18% chrome, 8% nickel, and very little of anything else except for a little manganese. And notice how quick it will measure once I pull the trigger. Start, and there it is. I can hardly release the trigger fast enough, and we've got that 304 stainless. You remember I said it was about 18% chrome and about 8% nickel, and you can see the chrome is reading 18.59 and the nickel is reading 7.99. And notice that it's right in the middle with the chrome between the 17 and the 20% specification for the recipe for this 304. The nickel is in range. Moly is reading 0.46, right in the range of 0 to 0.7. Moly is considered to be an element that's accumulated during a lot of recycling, so it's not normally specified, but it's always there. So we put in a specification for it. So now I'm going to measure a non-standard 304. That is, it's not a certified reference standard like these others. And so I pulled the trigger on this one, and there it is as a 304. And again, we see all the elements are pretty much in the range expected. Now, the second most popular stainless steel in the world is a 316 stainless steel. Here we've added in 2% moly. It's actually spec'd between 2 and 3%, but moly's kind of an expensive element, so it'll typically be near the minimum specification. Otherwise, it's got similar specifications for the chrome and nickel, that is, overlapping specifications, and you can see how quickly we got the answer on that one. And let's take a look at the moly, 2.16, right in the range where it should be. Let's take another one that's very similar to the 18.8 chemistry, that is the 304 chemistry, but it's modified with a little bit of niobium, actually only about 0.6 of niobium. It's called a 347 stainless steel. And here we see the 347 come up, and let's look at NB, niobium. It says 0.56. It should have been about 0.6. It is, and it's right in range. So we've got a really good match. If you notice in the upper right corner, it says good match 0.75. That indicates that between 0 is perfect and 4, calculated quality of match, is poor, and anything above 4 is a no match. So that's your quality of match number that guides you as to how good the match is compared to the specifications that it should be. Let's take another 18.8 type, 321 stainless. This one is modified with titanium, typically about 0.3% titanium. Otherwise, it's the same as the 304, and titanium is the lightest element we measure with the main filter. So it's harder to get on the quick measurements than it would be on a 304, where we don't have to worry about the titanium, but we still got it. It came out at 0.48, and it says it's 321, excellent match. So even nearly twin alloys like 304 and 321 can be measured quite rapidly. Now this one, 17.7, is similar to another alloy, actually like a twin. The other alloy is called 301 stainless, and that's a 17.7 chemistry, meaning 17% chromium, 7% nickel, but it has just a little bit of aluminum added in, nearly 1%. So how do we measure that? We have to have the light filter. Remember, anything above magnesium can be measured on the light filter up to atomic number 22. So we're going to start with the main filter. I've got it set to measure 3 seconds on the main filter, and then we'll switch to the light filter automatically. All I have to do is hold the trigger, or if it's a momentary touch, just leave it alone until it switches to the light filter, and I see that it, instead of calling it a 301, it now finds that aluminum and says it's a 17.7. So sometimes we need to allow it to go to that second filter. The training is included with every purchase of an XL5 Plus. So let's go now to, let's take a really high nickel alloy. This is an aircraft alloy, A286, and we'll just shoot that real quick, and you'll see how quickly that comes up. And notice the nickel, instead of being around 8%, the nickel's at 24%, right in the mid-range that it should be, between 23 and 27. Here's an interesting alloy. This is a pH, or precipitation hardened, 13.8. So that's 13% chrome, 8% moly in this case, with some lower levels of nickel in it. And the difference between this and most of the other ones we've looked at, with the exception of 17.7, is that it's got aluminum in it. Now, aluminum can be measured directly, as we said, by continuing to hold it for a few more seconds and allowing it to switch to the light filter. I didn't do that, but I still called it a 13.8 pH. Why? Because the rest of the elements are perfect fingerprint, and there's nothing close to that. However, it also tells you LEC, light element content, was not measured, but in that particular alloy, the specification calls for a nominal value of 1.12%. So it indicates that. If I wanted to, I could have held the trigger longer and determined that directly, but I don't need to do that in most cases. Here's an interesting stainless steel in that it's got tungsten in it. Very few stainless steels have tungsten in it. This is a Greek ascalloy, again an aircraft type alloy. And there it is, Greek ascalloy. And notice the W for tungsten, 2.53%. So it doesn't matter what elements are in there, any application for elemental determination in alloys where the element is above atomic number 12 can be done with the XL5+. I'm going to do one tool steel. This will be a high tungsten. It's a tool steel M2. And there it is, tool steel M2. And notice the tungsten, 6.6%. And one last one in the stainless steels, a knife blade. They're typically 410 stainless, which is a nice hardened stainless. And then we want the blade to be hardened so it stays sharp. And there it is, 410. So let's go now to the nickel-based alloys. Nickel-based alloys are much more valuable because nickel is a more expensive element than iron. So the base metal itself determines the value along with other alloying elements. It also is a higher temperature capability, so you'll see it in a lot of high temperature applications where it needs strength, hardness, and high temperature capabilities. Here's a pure nickel, or nickel 200 as it's called. And there it is, nickel 200, measured value is 99.95% nickel. And here is what's called a Monel. These are really good for marine applications because they're impervious to seawater, basically. It's called a K500, and it's basically high nickel with high copper, so 60-30 approximately. And there it is. We've got 65-29, along with a little bit of iron, a little bit of titanium, and so on. So Monels are very easy to do because all the heavy elements can be determined right away, and the light element aluminum that's in here is indicated by LEC, 3% aluminum. Interestingly enough, you can tell this apart from the 400 series, which is almost the same chemistry, with a magnet. It has a little bit of magnetic draw, and the 400 series doesn't. That aluminum seems to create some kind of a magnetic matrix in there. Here's a really high temperature alloy called a 718 aircraft again. 718 has high niobium. You'll see niobium here around 5% typically. That's the highest niobium of any nickel alloy I've ever run into. And it's kind of good to see that because the niobium has such a hardening effect and stability effect on the alloy. A very popular nickel is Hastelloy X. There it is. We're seeing that's about 50% nickel with a lot of other elements in there, including chrome, iron, moly. We would call these basically like superalloys because their characteristics are so good in terms of temperature, strength, and so on. Now here's a cobalt-based alloy, L605 or HS25, two different nomenclatures. So we put the more popular name, HS, Haynes Stellite 25, in the first place, and then we put the L605 in parentheses. And there you see a lot of cobalt, so that's a cobalt-based alloy, or a stellite. Here's a nickel base called C276, and that's a high temperature also. Waspaloy aircraft alloy used in the turbines. And now, the most interesting one, CMSX4, Canon Muskegon single crystal, number 4. This entire alloy is one single crystal as opposed to the thousands of crystal structure in all the rest of these. So it's a very expensive alloy. It's a very high temperature, very hard, high service capabilities for aircraft used in the hot side of the turbines. And there it is, CMSX4. And notice it's got exotic elements in there compared to anything else we've measured, tantalum and rhenium. You haven't seen those in any other alloys, but some of these superalloys will have that in there. So let's go to some low alloy steels now. I've laid out 4 or 5 here, and 4130 is one of the more popular low alloy steels. We'll shoot that first. There it is, 4130, and you can see it's all very low levels of alloying elements, which is typical of low alloys. Anytime the entire number of alloying elements gets above 5%, it's no longer a low alloy. So we know it's going to be all low levels. Here's a 4140, and separating that has actually been very difficult in the past. But because this has a new kind of what we'd call a hot rod engine in it, it's got a really high performance X-ray tube with high power. It gets that in seconds based on only a small difference in manganese. The manganese in this one's about 0.5, and notice the Mn here is about 0.8. And that's how we're separating that. Here's an F11, which is the one we use for testing and auditing the calibration because it's low levels of chrome and moly, 1.25% chrome and 0.5% moly. And there we see the chrome at 1.24 and the moly at 0.47, and the identification as a 1.25 chrome or a P11, which is the ASTM designation. I'm going to do one more here before I go into a couple of non-standard alloys. That is they're not certified standards. This is a Nitronic 135, or NIT 135 as we call it. And the difference between this and all the others we've looked at is you'll see LEC is at a high level, light element content, 1.66%. So this has aluminum in there, which is the light element that we haven't measured with the main filter. If I'd held it past 3 seconds, I would have picked up the aluminum. And I can do that just to show you the example. So let's let it go past the 3 seconds. And instead of putting a nominal value for aluminum, we'll have a measured value for aluminum. And there it is. It's about 1% in this alloy. So it's a little below the nominal value, but still within the specification. Okay, so let's switch to an alloy that is a piston made out of 11L17. That's a low alloy steel, but it's got lead in it for machining capability. It allows it to be machined easier. And there it is. And notice the lead about 0.27. Typically, we find that around 0.3. Here is a pipeline alloy, and it's a generic low alloy steel, so it won't give you a specific designation. There's thousands of these that are in the same range, but slight differences in the chemistry. And that one is a good example of a generic alloy. Notice that I had to grind it in one spot because it's painted, and we'll talk about that more later in terms of surface condition, but it does have to be representative of the alloy itself. Let's switch now to titanium alloys. Titanium alloys are widely used in the aircraft industry and other areas where you need a light but really strong metal. And the most popular one in the world, actually two I would say probably, are titanium CP, which means commercially pure, and so it should be near 100%, 99.86, and titanium 6-4, which is 6% aluminum and 4% vanadium. And there we have it. And notice that the LEC, light element content, says 6%. That's the nominal value. Again, if I held the trigger longer, it would have measured that directly. And let's take a look at one more, 6242. Here we have 6% aluminum, 4% zirconium, and 2% each of molybdenum and tin. Okay, so let's switch to the aluminum application. Aluminum alloys are widely popular now, and they're growing in application usage, not just airplanes, but we're trying to get more of them into cars and other things to reduce the weight and get better gas mileage and so on. So here is one of the more popular ones, an aluminum 1100, and there it is, aluminum 98.93%, and the balance of the elements, some iron and some copper. Now a 6061 is almost exactly the same, except slightly different levels of iron and copper, but we picked that up right away. So it's a very popular alloy that can be separated from 1100, even though there's very little difference, almost twins. 3003, here we pick up the name based on the manganese. Notice it's around 1% manganese. Here's a 2024, very popular aircraft alloy, copper, and there's the copper at 4.9%. Here's a 7075 aircraft alloy, which now adds zinc in. And then finally, a 7050. And the reason I picked the 7050 is that it's exactly overlapping specs, a twin to the 7075, with the exception of 0.1% zirconium. And watch how fast it picks that up. This always amazes me. There's a zirconium, 0.1, bingo. Last but not least, let's do some coppers. So pure copper, CDA 110, quite valuable for the recycle industry, electrical applications. 360, which is a high zinc. and 642. Now 642 is an interesting one because it's only consisting of copper and aluminum. Now you remember that aluminum can't be measured on the main filter. So when I start measuring this, it's not going to see the aluminum at all. It's going to think of it as pure copper. But if you could see this up close, you'd see a huge difference in the color between pure copper and an aluminum bronze, such as 642. So I know that's going to not be pure copper, even though the initial result is going to say ECU, electrolytic copper. So I have to hold the trigger longer to see what that yellow color is caused by, and sure enough, it picks up that aluminum, and it calls it a CDA 642 or C642. CDA is Copper Development Association, and we abbreviate it with just a C. And the last copper alloy, and this is interesting because this looks like it could be a stainless steel, a nickel base, a titanium, almost anything by the color of it. Why? Because this is a high nickel content in a copper matrix. So this is like, I believe this is like a 70-30 if I remember right. Yeah, 70-30, there it is. So almost 70% copper and almost 30% nickel. Last but not least, I'm going to shoot a pure molybdenum sample. And the reason I'm doing that is just to demonstrate that any pure metal can also be measured. It doesn't have to be a specific alloy, CP moly. So go to the website, which you'll see on the graphic, for a demonstration or information on the Thermo Fisher Scientific Niton XL5 XRF X-ray fluorescence analyzer. Handheld and extremely powerful. Thank you.